Hello guys, welcome back to Agora Math Circle's MathCounts training. This is session 11 of a 12-part series where we teach you everything you need to know about MathCounts so you can succeed on the MathCounts exam. My name is Mugil, Shanmugam, and I'm going to be presenting these videos for you guys. Okay, so let's get right into it. So, session 11 topics. What exactly are we going to be learning today? So, today we'll be covering the following broad topics: longest path and shortest distance, folding paper, which is basically just reflections, and problems with analytic geometry. Now, we do have some subtopics. We're going to be learning about traversability and transformations, some postulates and theorems about reflection, and finally some basic formulas and rules when it comes to geometry. Okay, so let's get right into it. All right, longest path and shortest distance. So before we go into how we can create the longest path between 2 points, we need to know what a traversable figure is. So a figure is traversable if one can trace each line with a pencil once and only once without having to lift the pencil. So you can trace this whole figure using your pencil and you don't have to lift your pencil. Now, basically, these figures, when they're traversable, that means that they have nodes in them. If you look at this diagram on the right for you guys, and you see these circles, right, that connect 2 segments or 3 segments or 4 segments, these are called nodes. So there are 2 types of nodes. The first type of node is called an odd node, and an odd node has an odd number of arcs connecting to it. So here, if you look at this node right here, it has 3 segments going out from it, or 3 segments connecting to it. So it's going to be an odd node. An even node obviously has an even number of arcs connecting to it. So these 2 nodes here, right, you see all these nodes that have 2 segments connecting to them, they will be even nodes. Now, a network is only traversable if, so you can figure out whether it's traversable if it follows these 2 rules, or if you can trace it completely with your pencil without having to lift the pencil. However, that's not really a reliable method because sometimes you may mess up, or sometimes you may not be able to trace properly. So it's best to just know these rules that you can use to figure out whether the network is traversable. So first, all its nodes are even. Basically, all of these circles need to be even. Basically, they can only have 2, 4, 6, 8 segments coming out from them. The starting and ending point can be any 2 nodes. So that means if my figure starts over here, then this can be an odd node, or if my figure ends over here, that can be an odd node. However, every other node has to be an even node. All nodes are even except 2 which are odd, the starting and ending point. So if you can satisfy these conditions with like a network, then you can make a path out of this network because the network is traversable. You can travel through this network without having to retrace your steps anywhere. A figure that can be drawn completely without taking the pencil off the paper or having to go over any line twice can only have 0 or 2 odd nodes. Why? Because this will be a traversable figure, so it can only have 0 or 2 odd nodes. And these 2 odd nodes would have to be the starting point or ending point of your figure. So basically, this is just really dealing with how a network is traversable, meaning that you can actually pass through this network, or you could use this network to fashion a path only if it follows these conditions, or you can draw through it, trace through it without overlapping or going over a line twice or having to retrace your steps. Okay. So topological transformations. This is another thing we need to know when we're dealing with the longest path or shortest distance. A topological transformation is the transformation of a figure into another with a one-to-one correspondence between the points of the 2 figures. So what this basically means is if you see this point on the cube, this point on the cube will become this point on the other figure of the cube. Basically, the reformed figure of the cube must have a correspondence with each point. You see these points over here, they will be duplicated in this one, however, they'll be in different positions. All the same, there's the same number of points in both of these figures. So that's what basically a topological transformation is. Here are the topological transformations of the edges of a cube, octahedron, and tetrahedron. So if you can see right here, we went over what octahedron and tetrahedrons are in the previous video, so go ahead and watch those if you haven't watched them already. But what I'm basically saying is these are topological transformations, how I'm transforming this version of the cube into this by simply moving the edges that have a one-to-one correspondence. I've done the same here, I've done the same here. Okay, so now that we've gone over what topological transformations are and what traversable networks are, let's move on to the next topic. So let's just go straight into a SIM problem now because we know the basics of this. So find the longest path from A to B such that no line can be traced twice. So no line can be traced twice. What does this mean? It's basically a traversable network. So whatever path you're creating, it has to be in a traversable network. So find the longest path from A to B. A is over here and B is over here, and no line can be traced twice. Each small rectangle is of size 10 by 5. Okay, so the long side is 10, and the small side is 5. And it's from MathCounts. So go ahead, pause the video here, and try to solve this problem. Okay, so hopefully you try to solve the problem. Let's go over the answer for this one. So for this network to be traversable, it can only have 2 odd nodes. Remember, we discussed this. And these can only be the starting and ending point. So we need to take out the edges of length 5 near the corner of the squares to get the longest path. So my starting point is going to be A, and my ending point is going to be B. So I want A and B to be odd nodes, but right now A and B are even nodes. So if you go back to this picture, you can see that there's one segment connecting here and one segment connecting here. 2 segments connecting at A and B. So right now they're even. I want to make them odd. So I'm going to remove this segment, and I'm going to remove this segment. So these 2 edges of length 5, if I remove them, then I have odd nodes as my starting point and as my ending point. So here we go. I've cut out my nodes, or basically I've cut out the edges over here, and now I have a proper path because I have an odd node as my starting point and an odd node as my ending point. However, inside this, there are still some odd nodes, so we need to remove those. We still have 12 odd nodes, and I've circled them over here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 odd nodes here, right? And odd nodes mean that they have like an odd number of segments connecting to them. We need to remove these because we can only have even nodes now that we've already established our starting and ending point. So we can make them even by taking out 6 edges of length 5. So if they have 3 segments connecting to them, if we take out 1, then they'll only have 2. Or if they only have 1, we can take that 1 out to make them only have 0, and so on. So if we do something like this, we'll make them all even. So we're going to take out 6 edges of length 5, because sometimes they share them, right? And here you can see the ones that I've taken out. 1, 2, 3, 4, 5, 6. I've taken out these 6 edges to make these nodes all even. So how many edges have we taken out total? Well, we took out 1 over here, and these 6. So then it's going to be 6 plus 2, which is 8. So 8 edges, and each of these edges was a length of 5. So 8 edges times 5 means we took out 40 units. They haven't really specified whether it's inches or centimeters, so we'll just call it units. We've removed 40 units from this network to make it traversable. So the longest path, well, first we want to calculate how much this whole thing has as perimeter, right? Because that would be the path. And then we can subtract how much we took out, because this is what we took out from the network. And then we get 120 is the longest path that we can use to get from A to B following these lines. So based on that, as you can see, it was pretty easy. All we really needed to do was make the network traversable, and then we subtracted what we took out from the total to get our longest path. Okay, so let's go into the next topic. So folding papers. When they talk about folding papers in MathCounts, it's really just testing your reflection skills. How well can you visualize how a reflection takes place? Can you visualize how a reflection happens? Can you visualize what happens to each and every point, and so on? So for that, we have some postulates and theorems that we can use to remember this. So there's a one-to-one correspondence between points and their images. So if I have a point here and I reflect it, then this is going to correspond directly to a point on the other side. If 3 points are collinear, then their images are collinear. So if 3 points are on the same line, basically, then their images must also be on the same line. If B is between A and C, then the image of B is between A and C. So when they say image, that means after reflection. So after I've reflected point A, B, and C, B should still be between A and C. The distance between pre-images, so the distance between the figure right now, equals the distance between the images after reflection. And the image of an angle is an angle of the same measure. Basically, this isn't really complicated. You don't have to memorize this or anything. It's basically saying that whatever you see in your pre-image, whatever you see before reflection, this should stay constant after reflection too. Finally, we also have the figure reflection theorem. If a figure is determined by certain points, then its reflection image is the corresponding figure determined by the reflection images of those points. So if I have a square and I'm reflecting that, first I can just reflect each and every point on that square, and that's how I get my reflected square, my image of that square. These are very simple. It's just a way to put into words what everyone mostly knows about reflection. Okay, there are some more theorems that we need. So perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of a segment. So a perpendicular bisector, what that basically means is a straight line, a straight vertical line that intersects a segment and cuts it into half. So if a point is on this line that cuts it into half, obviously it's equidistant. So there's the same distance from either endpoint to that point in the center. Basically, this line and this point are cutting the segment into half. The segment symmetry theorem basically says a segment has exactly two symmetry lines. Its perpendicular bisector and the line containing the segment. So here I've just drawn, or I didn't draw it out, I just got a picture of the perpendicular bisector theorem. So as you can see, segment AB, when cut by this perpendicular bisector here, this line, then M is equidistant from both points because it cuts the line directly into two, and they're both equal. So the segment symmetry theorem says that this is one line of symmetry, this line right here, and there's also another one. Line AB is a line of symmetry of itself. Angle symmetry theorem is the last theorem we really need to know about symmetry, and this says that the line containing the bisector of an angle. So if I have an angle and I have a line in like the middle that cuts it into two, then this is also a symmetry line of the angle. Wherever it says bisector, this means it's going to cut your angle, it's going to cut your figure, it's going to cut your segment into two equal pieces. So it makes sense that these bisectors are also symmetry lines of the angle. Finally, the symmetry line separates a shape into two congruent parts. The symmetric line is a perpendicular bisector of a segment with two symmetric points. All this is saying is basically when you have a bisector which cuts a shape into two parts, that's also a symmetry line because it's separating a shape into two parts, and each side is the same as each other. And it's the same principle as reflection. If I reflect this triangle over here, they're still the exact same triangle, even if I had a line of symmetry in between. Okay, let's go into a sample problem for this one. This one's not really complicated. All you need to keep in mind is how a reflection works and the theorems. They are pretty self-explanatory, so you don't have to memorize them. Just know how to apply them. In the figure below, triangle ABD, so triangle ABD, this is my triangle I'm talking about, is a right triangle with angle ADB. So angle ADB equals to 45 degrees. So this is a 45-degree angle. And BD is equal to 1. So this side BD is equal to 1. When triangle ADB is folded along line AD, point B falls on point B prime. This is point B prime. Basically, this is line AD. This triangle has been reflected over to create this. That's what they're talking about folding paper. So as I said, folding paper is the same as reflection for the MathCounts exam in general, right? Obviously, not every problem is going to be like that, but for this one, basically folding paper, they're just talking about reflection. They've reflected this triangle over AD. Now find the length of BB. So B prime. So BB prime is going to be this line. So you're going to have to draw on that line and then solve using what you already know. And this is from 20 more problem solving skills from MathCounts by JJ. Okay, so pause the video, go ahead and solve this problem. Okay, hopefully you paused the video and hopefully you got your answer. Let's go into how we can solve this one. So first, connect the 2 points I have, right? So I want to solve for B prime, the segment, and I just draw a line. I just drew a line here so I know what this segment is and what I'm solving for. Now we know all the sides are 1, right? 1, 1, 1, 1. This is a square because the triangle, first we can solve for the triangle. What we have here is a 45-degree angle, then there's a 45-degree angle over here, and there's a right angle over here. What this means is both the sides, both the legs are going to be equal. So if this one was 1, this one would have to be 1 too. It's just how it works because it's an isosceles triangle. So now that I know that they're both 1, then I know that this is just a reflection, so I know this is also 1, and this is also 1. This in totality is basically a square. 1, 1, 1, 1. All sides are equal. So now you may be recognizing, well, I know both the lengths of the leg. I can just solve for the hypotenuse using my Pythagorean theorem, which is a squared plus b squared is equal to c squared. So I know the length of the first square, or the first leg, which is 1. So 1 squared plus this leg, 1 squared. So 1 squared plus 1 squared is basically 1 plus 1, which is 2. So 2 is equal to c squared, which means c is equal to rad 2. So again, this is my a, this is my b, and this is my c. then you can just plug in both your 1's and you can solve for b prime is equal to rad 2. Again, pretty simple. All you need to do was recognize that this was an isosceles triangle with a reflection, and then it was pretty easy to solve. Alright, so let's move into our last topic for the day, analytical geometry. So we have different cases where you're asked to find the area and you need to apply geometry formulas. So we'll be going over some different cases and some different formulas you can use to find the area. So the first case you have is you'll be given an equation like this. A, right? So you're going to be given like A, absolute value of x plus B, absolute value of y is equal to C. It's just a type of equation, and since it's an absolute value equation, basically at the end you're going to get a rhombus. So when y is equal to 0, what will we find? Well, we're going to find that the two solutions of x are going to be c over a and negative c over a. And these two solutions are on the x-axis. You see one over here and one over here. So these are my two solutions. Now when x is equal to 0, y1, so my first y solution is going to be equal to c over b, and my second one is going to be negative c over b. That should not say n, that should be a b. So basically here you have one solution, here you have one solution. These two are both on the y-axis. This is when x is equal to 0. Similarly, I have two solutions here and here on the x-axis when y is equal to 0. So if I connect all my solutions, I get a rhombus. Now to find the area of this, I use this formula. 2 times c over a times 2 times c over b is equal to 2 is equal to 2 times c over a times c over b. So basically, if I know my y-intercept over here and know my x-intercept, the positive ones of course, then I can solve for my area. Basically, the two solutions times 2. I don't need the negative solutions for this formula in particular. So here, all we really need to do is find this y-intercept, the positive one, and the positive x-intercept, and then you can solve through the area formula. Now, there is another case sometimes when you're given a square, because it's a rhombus, right? But here we're given a square. So what this case is going to be is absolute value of x minus y plus absolute value of x plus y is equal to c. So similar to this one, but not exactly the same. Then again, I'm going to do the same thing when I solve for my x and my y. So when y is equal to 0, x is equal to c over 2. Y is going to be equal to c over 2, and that's when x is equal to 0, right? So I have my two solutions, one on the x-axis, and this one's on the x-axis, and this one's on the y-axis. So that now that I have my two solutions, I plug into the same formula, but this one's going to be a little different. So here I have 2 times c over 2 times 2 times another c over 2, right? Because both of these are actually going to be the same value because it's a square, then I'm just going to get c squared. So here, my area formula is simply c squared. And if you really think about it, c here is just my side. So normally when we have a square, we find the area by just squaring our side. And here we're basically doing the same thing, except here we have an equation form. So basically this is just a long drawn out way of kind of proving how we find area of different shapes. Generally in the MathCounts exam, sometimes you'll just be given the direct shape with the side or the length you need, but sometimes you'll be given an equation like this or like this, so it's handy to know how to solve it using this. Okay, let's move on to a few more formulas. So sometimes you'll be given the coordinates of the vertices of a parallelogram and asked to find the area. So here A, B, C, and D are 4 consecutive vertices of a parallelogram, which looks kind of like, I'd say a rectangle, but it has like slanted sides. And E is the point of intersection between AC and BD. AC and BD are my diagonals. So E is going to be the point of intersection between these two diagonals in my parallelogram. And the coordinates of A, B, C, and D are going to be XA, YA. So this is my coordinate of point A. And B is going to be XB, YB, and so on, right? So here's the formulas that I can use for solving. So x of E, so the coordinate of point E, the intersection, is going to be 1/2 of XA plus XC, which is equal to 1/2 into X subscript B plus X subscript D. I'm just saying XB and XD because it's quicker to say, but you should really say X subscript B, X subscript D. Anyway, to solve for the Y coordinate of the intersection, which is E, right? So when the two diagonals intersect, that's how I'm getting my E. I found the X coordinate using this formula. My Y, to find the Y coordinate of this, I'm going to use 1/2 of YA plus YC, which is equal to 1/2 of YB plus YD. And again, here, both of these formulas work. Basically, we've given you two alternatives for each one. You can use whichever one works for you based on what you already know. Sometimes you'll be given the coordinates of B and D, but you don't have the coordinates of A and C. Well, then you can just use this formula to find the coordinates of your E intersection point. So basically, x subscript A plus x subscript B is equal to x subscript B plus x subscript D, and similarly, the same thing applies for the y's. So the coordinates all add up so you can find each other. So if you know the x coordinates of A and C, you can find the x coordinates of B and D, and so on. So like that, this is basically how you can solve for the different coordinates, different vertices of parallelogram. Now, sometimes you'll be given a line and asked to find a parallel or perpendicular equation. So given an equation of form ax plus by equals c, first convert to form y is equal to mx plus b. Obviously, there are formulas you can use, which is ax plus by, but for me personally, I just like to convert to y is equal to mx plus b, so whichever one works for you. Now, a parallel equation will have the same slope m. So basically, y is equal to mx plus b. I'm going to have the same exact m value here. My b will just be different. A perpendicular equation will have an opposite reciprocal slope. So what that means is if my slope here is, like, just say 2, right? My perpendicular equation slope is going to be negative 1/2. So I change the sign and then I flip it. So I get 1/2. So this is a quick way to find your parallel and perpendicular equation. You can also use this formula for your parallel and perpendicular. So ax plus by minus ax initial plus by initial is equal to 0. So here y0 and x0 are basically just your initial value of x and y. Here probably intercepts. And similarly here I have bx minus ay minus bx0 plus ay0 is equal to 0. This is for perpendicular. So the first one's for parallel, the second one's for perpendicular. And basically, sorry, I misspoke earlier. Basically, x0 and y0 here are probably the point they're already given you to solve with. They'll be like, find an equation with this point on the line. Then you can use, and you can just plug in the points you already know, and then solve for the equation. But personally, I like to use the ones above that are just using y is equal to mx plus b. Choose whichever one works for you, and whichever one you can do faster, but really efficiently, and you get the right answer with. Okay, and here we have a few more formulas. So this one's midpoint and point in between. So the midpoint formula is basically P would be the midpoint of segment AB, and the coordinates of P will be x1 plus x2. So the coordinate of A plus the coordinate of B, the x coordinate of the both, over 2. And the next one, to find the y coordinate of P, it'd be the y coordinate of A plus the y coordinate of B over 2. So basically, it's very simple to remember: x1 plus x2 over 2, y1 plus y2 over 2. Now here, this is for the in-between formula. P is a point on segment AB, between A and B. So here, P was the midpoint. It was directly in the middle. But here, P is just somewhere on there. It doesn't have to be in the middle. So then lambda is going to be equal to AP over PB, and x is equal to x1 plus lambda x2 over 1 plus lambda. Here, y is equal to y1 plus lambda y2 over 1 plus lambda. So basically, once you solve for lambda here, you can find the coordinates of this point in between. But to know that, first you need to find the distance between A and P and the distance between P and B. Okay, so make sure to keep these two straight because one's for the midpoint and one's just for a point somewhere in between. It doesn't have to be the midpoint. All right, so here we have calculating the area of a polygon in the coordinate system. So this is the more common type problem that you'll see on the MathCounts exam. So we have a triangle and we also have a quadrilateral. We'll solve for a triangle first. So here your vertices are going to be x1, y1, x2, y2. This should be a y2, and x3, y3, and so on, right? So basically, well, not so on for this one, only 3. But this is just your generic names for your coordinates until you can solve for them. So your area is going to be 1/2 into the absolute value of x1 into y2 plus x2 into y3 plus x3 into y1 minus x1 into y3 plus x3 into y2 plus x2 into y1. There's not two minuses, this one's just extraneous. And the absolute value of all that. So basically what this is saying is if you know the different parts of the coordinate and you just multiply them all together, then you can just find your area pretty quickly. But for that, make sure you know all your coordinates, all your x values, and all your y values. All you need to do is just plug in, multiply here, subtract, and then find the absolute value, then multiply that by 1/2. So obviously for a quadrilateral, you're going to have a similar formula. It's just going to be a little different. So a quadrilateral will have 4 vertices. Sorry. So it's going to be x1 and y1, x2 and y2, x3 and y3, and x4 and y4. And the area of all this is just going to be your similar formula here, but you're going to do x1 into y2 plus x2 into y3 plus x3 into y4 here plus x4 into y1 minus x1 into y4 plus x4 into y3 plus x3 into y2 plus x2 into y1. And the absolute value of all this. And this is going to be multiplied by 1/2. So these two formulas can get a little confusing because they are very similar. Make sure to keep the two separate. And the way you do this is just when the quadrilateral formula has this extra y4 term and x4 term because it has 4 vertices. And all this you just use to find the area of the quadrilateral or triangle if you're given your vertices. So in this way, it's a quick way to just find your area when you're just given a figure on like a graph. All right, so let's apply it. So the points -5, 5, 2, 6, and -2, 2 are the vertices of a triangle in a coordinate plane. What's the number of square units in the area of triangle ABC? So I have my points A, B, and C. You know the coordinates, plug into the formula, and you can find the area. And that's from the 1997 MathCounts National. So go ahead, try to solve this problem. Okay, so hopefully you pause the video and you try to solve the problem. Let's go into how we can get the answer for this one. So this one was just plugging in. So 1/2 into the absolute value of x1 into y2 plus x2 into y3 plus x3 into y1 minus x1 into y3 plus x3 into y2 plus x2 into y1. So when I plug all of that into my formula, I'm going to get -30 plus 4 minus 10, which is basically -36. And here I'm going to get -22 plus 10, which is -12. And then here I go, minus here. So minus -12, which is just 12. So -36 plus 12, well, that's going to be -24. But this is absolute value. Rand's absolute value, so I'm going to get 24. 1/2 times 24 will give me 12. So again, here you just need to plug into the formula. And there is an extraneous minus here, so I apologize for that. There's only one minus sign. All right, so that one was pretty simple, just plugging in our coordinates, and then we get our answer of 12 square units of area. Okay, thank you guys for watching. Please like and subscribe if you enjoyed the video, and leave a comment with any questions you may have. Thanks for watching, and stay tuned for the 12th video, the final video. See you guys.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!